Hello. So today I'm going to talk about velocity and acceleration of a point in a rigid body. Remember that. Remember that you started with this frame. This was our inertial frame. Then we said that, all right, so what if I have a secondary frame placed at O prime? Let's say this is O prime. And then I have defined a frame with second set of unit vectors. So what I have here is, so I defined it as E hat 3, I think, E hat 1, and E hat 2. Alright. And then we said that, alright, so what if this secondary frame, the easiest case is when the secondary frame only translates with respect to primary frame or inertial frame. And if it happens, then every point, and let's say that this O prime is attached to this body. So every point, if the secondary frame only translates with respect to inertial frame, then all the points, because it's a translation, have the same velocity and acceleration. And then we move to rotating frame. We assume that what if the secondary frame rotates about the primary frame? And then we derived two equations for velocity and acceleration. So that, now, in this case, we only consider rotating frame. Note that, all right, so if you have a translating and rotating frame, all we need to do is to add the component of translation to our final velocities and acceleration. Meaning that, all right, so this is what we did. We had R double dot equals to R circle, double circle. This was the equation we derived for acceleration, plus 2 omega cross R circle plus omega dot cross R, and R was this R, all right, R, and this is P, an arbitrary point, plus omega cross R. Now, when we derived this equation, we didn't say that point P need to necessarily be on a rigid body. It could be on any body. It could be on an elastic, deformable body. So it is the relationship between a primary inertial frame and a secondary rotating frame. And the secondary rotating frame, the rotation of the secondary frame is characterized using this rotation matrix. And we also derived an equation for, we started with an equation for velocity and then we went to acceleration. This is a circle. Plus omega cross R. All right. Now, question is, what happens if this point, point P here, be on a rigid body? So what changes in this relationship if our point in a rigid body? So we said that by definition, when we say rigid body, it means that the distance between the 2 points on that rigid body does not change. As the body rotates or translates, rotates and translates, the distance between the 2 points on the body does not change. That's a rigid body. So if the distance between the point P and O prime does not change, what does it mean? It means that if I differentiate R with respect to time in this frame, in prime frame, that goes to 0. And that's what circle or circle represent. That's relative velocity. That's how fast the distance of P changes with respect to O prime. But this is a rigid body. The distance of P with respect to O prime does not change. So our circle goes to 0. So velocity and acceleration of a point in a rigid body. So when R represents the position of a point in a rigid body relative to O prime, so as I just explained, when R represents the position of a point in a rigid body, all right, relative to O prime, then O prime is the origin of our body in attached frame. So I'm attaching O prime to the body. So both P and O prime are points in this rigid body. So then, by definition, R circle goes to 0 and R double circle also goes to 0. Essentially, R with P with respect to O prime is a fixed parameter. Right? So the length, the time rate of change of R is equal to 0. So what does it mean for these two equations, right? So if R circle and R double circle go to 0, it means that I have R dot equal to omega cross R. So these velocity components are the velocity components due to rotation of body attached frame. So if the body attached frame translates, you would add a term on the right hand side, right? Translates and rotates. That's pretty easy. So that's pretty straightforward. So the body attached frame, this rotates. And then for acceleration, we have 2 omega cross 2 omega cross R circle plus omega dot plus cross R plus omega cross R. So in acceleration, we have two terms. All right. So one term we just talked about, this goes to 0. But this term also goes to 0 because our circle goes to 0. Again, what was this acceleration? This was Coriolis acceleration. So Coriolis acceleration goes to 0 too. Right? So this also goes to 0. And our acceleration simplifies to only two terms. So acceleration simplifies to only two terms. And we said that this is tangential acceleration, and this is centripetal acceleration. And it is common to replace omega dot with alpha. So you could see this equation in this form: alpha cross r plus omega cross omega cross r. All right, so alpha is angular acceleration. All right, so now that's one thing, one last thing. Why would we call these two terms tangential and centripetal? Think about how this cross product affects the direction. Not affects, but how does it determine the direction of each of these terms? Meaning that, let's say, for example, my omega and omega dot both were pointing out of this page. Let's just assume that, just for the sake of demonstration, omega points out, omega dot, because these are vectors, points up. And r is on the plane. Then, using right-hand rule, omega points up, r points in this direction, so my omega dot cross r points in tangential direction. Same thing here. Omega cross r is tangential direction, but then you would pre-cross multiply that by omega, and that makes it an acceleration pointing towards the center of rotation. It is exactly the same thing as we have in tangential normal frame. All right, this was today's lecture, and see you later.